In the previous lecture, we discussed that the quantum transport refers to the manifestation of quantum mechanical properties of charge carriers, especially electrons and holes, in transport properties. And we also concluded saying that this quantum transport generally refers to the transport through low dimensional systems or mesoscopic systems, where the quantum confinement effect on the electrons are apparent. So before we dwell into the details of quantum transport, let us quickly revisit the classical transport, okay? And in that framework of classical transport, let us make incremental progress, incremental changes to various parameters, various terminologies, various quantities, and we will treat the transport on various low dimensional systems one by one. Okay, so in this lecture, we will look into the classical transport briefly, then the Fermi-Dirac distribution and density of states. So first, let us look what do we deal with, or what kind of mechanism we deal with when we discuss classical transport. Here, the electrons are treated as the molecules of an ideal gas, and the statistics that these particles or these electrons obey are Maxwell-Boltzmann statistics. So what we have is an MB statistics. So what I have here is a representative system. The blue colored region is the system, and the yellow color regions are the contacts where you apply voltage and measure currents through. Okay. So in the premise of Maxwell-Boltzmann statistics, what we have is we have a box which represents the solid, and there are a lot of scattering centers in the solid. There could be scattering between those electrons, so scattering with some other scattering centers such as impurities or whatsoever, but those details are not really relevant here. The point here is these electrons undergo motion very similar to the ideal gas molecule. It undergo collisions, and it will move from one end to the other end by the application of electric field with an average velocity Vd. That is a drift velocity. So the way it is defined is, if you look at this plot here, every event of collision will reset the momentum of these electrons to 0. So in one case, electron will go to a certain distance and come back to 0. This is the velocity and this is the time axis here. Then maybe next time it will go further distance and undergo a collision and come back to 0. So each of this drop here refers to a collision, and the electron velocity is reset back to 0. So you will have a distribution of time between two collisions, this delta T1, delta T2, and so on, delta Tn. And this mean or the average of the time is something which we call the collision time or scattering time. That is the mean time between two collisions. And correspondingly, there is an average value for the velocity for the electrons through the system that we define as drift velocity or Vd. Okay, so you have a number of electrons and number of scattering events. So the statistics works pretty accurate here. So what you have is you have certain velocity, an average velocity by which the electrons move through the system, and the whole process is dominated by scattering or collisions. Okay, and tau here is the mean collision time. Now you can build on to this framework, and you can say that the momentum is basically h bar into delta k, but delta k is nothing but the wave vector that has been built or that has been accumulated after one collision. That is nothing but depends upon the force into that delta t, that is the time after the collision. Okay, so over delta t time there is a force F, that is F is E into E. Okay, and but average delta t is tau. So what that means is this momentum, average momentum each electron has is something like minus E tau. That's what it is. And this velocity attained is P by M, that is E tau by M. Okay, and from this you can calculate the current density, which is charge density into velocity, that is N into E into Vd, where Ne is the charge density, N is the number of electrons per unit volume, Vd is the velocity, and that is going to give you Ne square tau by M. E is our sigma is the conductivity. This is your Ohm's law. Okay, this is nothing but the Ohm's law. That's what this is. This is another statement of Ohm's law. The usual statement that you know is VE is equal to I into R. That's the usual statement. So that is simpler statement. And this is the statement which you get from the by treating the transport as classical Maxwell-Boltzmann statistics. Okay, and this model is actually called the Drude model or Drude picture. Okay, now in this case, what we have done is we have considered that there is a connection which is made by the source electrode and the drain electrode. There's a source electrode here and there's a drain electrode here, and the electrons are actually moving through the system. Okay, but now there are a lot of interesting but crucial details that we have actually swept under the carpet in this case. So there are a few points that you need to consider. One is, which is very, very important to consider, one is electrons are quantum mechanical entities. So this Maxwell-Boltzmann statistics is something which you cannot apply all the time, because those are electrons are fermions and you need to apply Fermi-Dirac statistics. Okay. Secondly, you basically assumed that just by connecting a source and drain leads the material, the electrons will freely flow from the source to drain. But there are few other factors that are crucial or that one need to consider when we look at this transport. Number one, what is the nature of this interface? Okay, this is not like a simple, barrier-free or resistance-free interface. Whenever you mix, whenever you join two different materials, so two dissimilar solids, you always will have some kind of impedance or some kind of barrier, some kind of resistance, and the behavior of the resistance as a function of the applied voltage is also varies from situation to situation. Okay, that we have not considered. Secondly, if you look at the microscopic picture of the electrical transport, what happens is you have an electron which is going from the source, which is the material, then that electron eventually will go back to the drain. Okay, so source and drain are basically huge collections of material which actually can accept or emit or accept respectively indefinitely with any number of electrons. Okay, so what that means is, and the material, or in this case the blue region here, need to have space for the electrons to go. When I say space, if you look at the whole thing, I have represented here in terms of energy axis. Okay, here it is this axis energy. This is a physical space. This is a physical dimension, but here height here represents energy. So when you apply a source drain voltage, what you are going to have is you are going to apply you are going to tilt the whole potential or energy landscape in this picture. So what you are going to have is you have a small slope here. Okay, now the point here is you need to have electrons available in this region. You need to have space for the electrons available here to collect those electrons. Okay, and you should have space here. When I say space, this all refers to space in the energy space or in the energy axis. There should be space or states available here. States, that is the term. Okay, here also everything refers to state. States, here also what I am saying is state. So there should be electrons available here. There should be states available here, and there should be states available here for those electrons to traverse through. All these plus this region in the middle should not basically pose a huge resistance or non-trivial behavior for the transport. So all these things are very, very crucial for us. So let us now try to understand the role of each of these and how we can factor in these details into our basic framework of classical transport. That is what we will do next. Okay. Now let us look into the quantum mechanical treatment of the electrons, which is the free electron theory in its most primitive form, which is an incremental change to the Drude's theory. Here we are treating the electrons similar to the particles in a box problem in the quantum mechanics. We know that the wave vectors for a particle in a box, in a three-dimensional box, as shown here, are given by kx is 2 pi nx by L, and similarly for ky and also for kz. Okay, where this nx, ny and nz are quantum numbers. The total energy is h bar square k square 2m. It is only the kinetic energy. There is no potential energy because the assumption is the potential energy inside the box is 0, where the k square is given by kx square, ky square and kz square. And you can note here that this is actually an equation for a sphere or a spherical surface with a radius given by k, and this sphere in the k space, which represent the k states of electrons inside the material, inside the solid, is called Fermi sphere. And the volume occupied by the states in the Fermi sphere is basically given by 2 pi by L in each direction. So that will 2 pi by L cube. That will be the volume of a state. Now, the total number of states in the Fermi sphere is given by the volume of the sphere divided by the volume per state. That is 4 by 3 pi kf cube divided by 8 pi q by L cube. That is the total number of states inside the Fermi sphere. And if there are n electrons in the system, okay, if there are n electrons in the system, then the total number of states that would be occupied or that in the Fermi sphere, inside the Fermi sphere, will be n by 2, because in this case we have not considered the spin degeneracy. So every state, every k state can actually take 2 electrons. So if you account for that 2 factor, you can know that the total number of electrons in the system is given by kf cube L cube divided by 3 pi square, and where kf is the radius of the Fermi sphere, where kf is also the highest occupied state, that will be kf in the Fermi sphere. So the radius of the Fermi sphere is kf, which is given by this expression 3 pi square n by L cube 1 by to the 1/3, or 3 pi square ns, where ns is the concentration or the electron density in the system, okay, to the power 1/3. So the radius of the Fermi sphere is given by kf, that is called the Fermi wave vector, okay. The radius of Fermi sphere is called the Fermi wave vector, and the energy of that state with the wave vector kf is called Fermi energy. Alright, so this is the overview of the most simplest quantum mechanical treatment of electrons in the solid. Okay. Now, we got an expression for the number of states in the Fermi sphere and the highest occupied state. Now, the electron transport through the system also depend upon whether there are states available inside the material. So even if you try to inject or try to transport electrons through the system, but you also need to make sure that there are states available at that energy. So the action of you putting an electron in the system in transport in practice is you apply a voltage between the source and drain. That sets the energy scale. And the question now is, are there states in the material so that electron can go through those states to the drain side from the source side? So that is defined by a quantity called density of state. It is nothing but the number of states per unit energy per unit volume. Number of states per unit energy per unit volume. That is called density of state. And that is given by the expression dE. This quantity here accounts for the unit volume, and dN by dE here, that is the number of states per unit energy, and this is for unit volume. And from our previous view graph, previous slide, we have expression for N, and this you can use this Kf, that wave vector, and convert that into energy units, and you can write this N in terms of the energy, okay, using this expression. Now all you need to do is you need to take the derivative of N with respect to energy and divide by the volume, okay. So then this L cube term will cancel out, and you will get eventually the expression for the density of states, and this is for a 3-dimensional solid. So that is why you put L cube here. For a 2-dimensional solid, you will replace this L by 2. For a 1-dimensional system, you will replace it by 1. Okay. And correspondingly, there will be changes in the Fermi wave vector also. That also you need to consider. So what we are saying here is the density of states for a 3-dimensional system is proportional to e to the power 1/3 or square root of E, square root of energy. Okay. So this curve here represents the density of state as a function of energy for a 3-dimensional solid. Similarly, you can also get expression for the density of states in reduced dimension, which is the reduced dimension. Transport through reduced dimension is our topic of discussion throughout this course. Okay. So for a 3-dimensional system, we know that it goes like square root of E, or is given by this curve there. For example, I have a picture here of graphite. So as an example, this is a 3-dimensional system, graphite. For a 2-dimensional solid, by substituting appropriate the right Kf and the right volume in the previous derivation, we can get that this density of state is actually a constant for every subband. These represent different subbands. So inside each subband, it is actually constant. For example, you can peel a sheet of carbon atoms from this 3-dimensional graphite, that is called graphene. There are a lot of other examples also, semiconductor heterostructures, quantum Bell systems. There are many examples for 2-dimensional systems, interface between two materials. Okay, these are all 2-dimensional systems, and in 2D, it is actually a constant. In 1D, for example, a carbon nanotube CNT or nanowire, it is proportional to 1 by square root of E, or the density of state, which is given by this spiky structure there, and that goes like 1 by square root of E. And for quasi-zero dimension, such as quantum dots or conducting nanoparticles, that goes like delta function, delta of E, and that is given by these features or these delta functions there. For example, the C60 molecule is actually a quasi-zero dimensional system. Quantum dots or nanoparticles, these are all examples of 3-dimensional system. The 3-dimensional confinement or 0-dimensional system. So, and for these confined systems, we know that the density of state actually has different dependence on E. So density of state is one of the main quantity which controls the transport, or main parameter which controls the transport through the system. And you can see that as you change the dimension of the solid, the density of state changes, and the behavior of transport also will change, which you will see when we discuss transport through all these 2-dimensional, 1-dimensional, 0-dimensional systems as we make progress in this course. All right. Now, there is one small detail which we need to discuss. This is also something which most of you guys have actually done in one of the previous courses, such as solid state physics or statistical mechanics. That is the occupational probability. So here what I have drawn is a two-dimensional Fermi surface or a two-dimensional system. In 2D you will get a Fermi circle or Fermi, it's not a Fermi sphere, it's a Fermi circle. And Kf is the Fermi wave vector. And the Fermi Dirac statistics, that is what the electrons as quantum mechanical entity as fermions follow instead of the Maxwell-Boltzmann statistics, which is what the Drude theory assumed. Okay, so these Fermi Dirac statistics, or the Fermi Dirac function or Fermi distribution function, which is given by this equation there, that is going to tell you what is the probability that certain state is empty or that certain state is occupied. Okay, and that probability also changes with temperature. For example, here this is the energy axis. Okay, this energy goes like this, or that is same as saying energy axis is energy increases as you go from the center of the Fermi sphere to outwards. In this direction, energy will increase. And at zero temperature, at absolute zero, the state until the surface of the Fermi sphere, that will be filled with a probability 1. This red curve, the red trace represent that, or the blue trace here represent that. And every state above the energy of EF or the Fermi energy will be unoccupied, will be available for transport. Okay. So as you change the temperature, this step function is going to get smoother and softer, and this is going to develop a width, which I have represented here. This is going to develop a width where some of the states within a energy width of 4 kBt, that is the width of the Fermi function, that is approximate width of the Fermi function, that will be available within that window, will be available for transport. That is a temperature broadening, which I have represented here by the black curve, where the blue trace here represents the picture at zero temperature, and above zero temperature, or when the temperature is not zero, this blue trace will get softened, or here the red trace will get softened, and that will develop a width to the distribution instead of the sharp cutoff for the probability. And the states within that energy window around the Fermi sphere will be available for transport. And this Fermi energy, if you look at what is the quantity or what is the magnitude of the Fermi energy, that is approximately equal to the ionization energy of the solid, because these electrons are free from their parent atom in the solid because they are ionized. So you can think that the freely moving electron, those are the electrons on the surface of the Fermi sphere, and those are the electrons which got free from the parent atom in the constituent solid. So the energy of those electrons should be comparable to, in principle, should be comparable to the ionization energy of the solid. So if you look at that, will be like 10 electron volt in that order. I'm not saying it's an accurate number, but in that order, 10 electron volt, because you know that the ionization energy of hydrogen atom is 13.6 electron volt, that we know. So what I'm trying to say here is the Fermi energy is of the order of tens of, close to say 10 electron volt, and the width, which is 4 kBt, if you look at the room temperature, that approximately correspond to 100 milli electron volt, because kBt at room temperature is 25 milli electron volt. Room temperature correspond to 25 milli electron volt. We can multiply the Boltzmann's constant, the temperature in Kelvin scale, that will give you 25 milli electron volt. So the width of the Fermi distribution is 100 milli electron volt approximately. That is the broadening of the Fermi distribution. But the Fermi energy, which is actually a very, very large number, it is more than 10 electron volt. It's a huge number, it's a large quantity compared to the width. So what you can say here is the electrons which are available for transport, those are the electrons on the surface of the Fermi sphere within a width of 4 kBt at a temperature T. That width is comparatively very, very small compared to the overall energy or Fermi energy of the solid, which is 10 electron volt, whereas this is only 100 milli electron volt. So a reasonable temperature, whether it's room temperature or even slightly higher temperature, the softening of this the Fermi surface is not really appreciable. That contributes only like a small fraction of the overall dimension of the Fermi sphere. That is what I'm trying to say here. All right. Now we have went through the basic elements of transport, and let me summarize here what are the things we discussed. So this is our candidate system for transport, where we have source and drain. Okay, there is a source side and there is a drain side and there is the material here. But what we have not considered in this discussion, when we look to the classical treatment or Drude's theorem or Drude's treatment or Ohm's law, is number one, the availability of electrons on the source side, that is given by the Fermi distribution of the source side. Okay, and secondly, the availability of states in the system. That is nothing but the density of states, d of E. Okay, and three, whether there are states available on the drain side. So this is the source side, this is the drain side, source side, drain side. So we need to look at two factors. Number one, are there electrons available here? Are there empty states available here for these electrons to go and sit on the drain side? And are there states available here? That is the density of states inside system for the electrons to go through, for the electrons to traverse through. And if there are states, what is their behavior as a function of the energy? And that also we discussed in the previous slide, where this as a function of energy, the density of states shows different behavior depending upon the dimensionality of the system. Okay, so the third thing what we are saying here is availability of states on the drain, that is 1 by f of e, 1 minus f of e. Okay, because f of e is the probability of state being full, and 1 minus f of e is the probability that a state being empty. So there should be an empty state on the drain side for this electron to go, and there should be a state which is full here for the electrons to start from, and there should be a state which is empty here, that is given by 1 minus f of e on the drain side, and there should be states available here for the electrons to traverse through. So these three things need to satisfy. This is the states available on the drain side, states or number of states available in the system, and the electrons available or the charge carriers available on the source side. And another small thing, it's not a small thing, it's actually a very crucial thing, but which we have not discussed, is the behavior of this interface. So generally, the leads which we refer as source or drain here, those are metals, and the system usually would be some other phase, such as semiconductor or semi-metal or superconductor, something else. So what is the nature of the interface? That is something which we need to worry about. Nature of the interface. That is also an important aspect. That's an important, very important aspect. So what we will do now is, we will look these features in detail for various dimensions. And in the next session, we will start with the fourth one, the nature of the interface between the leads which injects or takes electron out of the system and the system. That is the focus of our discussion for the next couple of lectures. All right.